Hi, Raphael. How are you?
Hello, can you hear me?
Yep, I can hear you well.
Okay. So
How are
how
you
does
doing?
this exactly work then? Is there
So,
a camera option here or something?
no, there's no camera. It's just audio.
Uh-huh.
So, do you want me to? Hi, Victoria. How are you? Meet Raphael.
Hello, Raphael.
Hi.
Hello. I'm good. I'm driving, so we'll hope that.
Okay.
Uh, nice to meet you. Hello, Katarina.
So, yeah. Hi. um. So I in the chat I put the paper for now, and then the static slide option. Do you want, so we have an option on top of the room, so right, instead of just in the chat on top to share links. So should I put the Google Drive folder that has also the videos in there?
Yes, yes, I think
Okay,
that's fine.
then I'll do that. And yeah, if you want to try if that works. So since it's not video or screen share, it's really helpful if you just say, go to the next slide when you switch
Okay.
to the next slide. And then if you're on the slide that has the video, you could say, now if you can see the slide on the PowerPoint presentation,
Okay.
open this movie, and then that should work. People are used to it because we had a few presenters that had very large PowerPoint presentation with a lot of videos, so that's how we kind of solved it. So
Okay.
yeah, we have still 5 minutes, so we still have some time. I hope everything is good.
Yeah,
Your
me
your
too.
start
First time with
well.
this platform, so yeah, it is different to the typical Zoom meeting, right? Like where you share directly your things.
Yeah, so this
So
is like a public social media
mm,
event. So I don't know if you know Twitter Spaces or anything like that. It's like we don't like it's a public room. Anyone can share that's currently online on Clubhouse. And on Zoom, you would need to know the email
yeah.
addresses of
Okay.
people, and yeah, so and
Sounds
then
good.
we record the session if that's okay with you.
Yes.
Yeah, so the links, the good thing about what I like about the Clubhouse recorder is that the links to the PowerPoint and all of this stays active in the replay. The only thing you
Okay.
cannot do is ask a question. That's why. And then there's this option to switch, like when somebody asks a question that you maybe know the answer of or something, you can just switch to the next person really easily on the recording.
Okay. Great.
Okay. Yeah, we will start soon. Hi, VTR, how are you?
Hi, I'm good. Thanks for bringing me on stage. I'd love to hear more on this topic.
Yeah, wonderful. I'm glad. And yeah, welcome everyone. We'll start in a few minutes, so feel free if you know somebody that would be interested in this topic, feel free to share. I'm going to share now on Twitter that we are starting now. And yeah, I think it's really interesting. And it's also, I always love topics that I don't know much about. So, yeah.
That's why we're here to
Yes,
learn.
exactly. I agree.
That's our enthusiasm.
Yeah, we can't hear you, Victoria, but I agree. We heard that's why we're here. So, um, yeah, I think since we started this club, I think since I haven't learned so much in a year. since I was probably undergrad student, like from such a broad range of research. So it's been really interesting. Yeah, we'll start in a minute. I know people will still keep coming in, but that's okay. We can start with introductions and then go from there. So it will be good. So yeah, just to say ahead of time, in the chat there's a link to the paper. One is the free version, it's the preprint version, and then the other one is the science publication, which is, you know, not free, or it's behind a paywall. That's why I shared both. And then there's also a link to a Google Drive file where there are no videos in the file, so the file is smaller. And then on top of the room is pinned a Google Drive folder where I split the PowerPoint file because it was kind of big with the videos in two. And in case the videos will be really slow in the embedded version, I also uploaded the movies. So Raphael will refer to them, and then you can maybe, if you would like to see the movies easier, then just switch to that file. And the videos are really nice, and the presentation is really beautiful. So you should you should take advantage of having all the files there. So okay, I think we can start. It's 7 p.m. EST. So welcome everyone to Science Society, and of course a special welcome to you, Raphael. I hope I'm saying your name right. I'm probably saying the
Yes.
Portuguese version. And just so that people get to know you a little bit better, Dr. Rafael Luque is a postdoc at the Instituto de Astrofísica de Andalucía in Spain. And he did his bachelor's in physics at the University of Granada in Spain, and his master's in physics at the University of Heidelberg in Germany. And yeah, he is working in this field after his PhD since 2021. And usually since Victoria, her internet connection is not perfect, I'll just try to in front of her do a good job for the interview, because that's her part. And we usually start by asking, how did you discover that you want to follow the path of science? Was it something you maybe always wanted to do, or at some point in your life you, I don't know, had an interesting class, read a book, or something that sparked your interest and
Well, I
you?
think my interest came when I was a kid. I don't know. I think I was 11 or 12, and they in my village they did a astronomy course or something. It was for adults, so my father went and he took me with him because I was the one who wanted to go, and I was really hooked up with all the astronomy concepts that they show us in this course. And afterwards, we did an astronomical observation with the small telescopes and everything, and I was really excited about it. Afterwards, after some years, 16, 17, I started going out with a telescope that a friend had it, and we went to observe a lot at night and not discover anything, right? Like, but getting to know different objects in the night sky, the constellations, nebulas, galaxies, and so on. And then when it came the moment of deciding to go to a university career, I wanted to do physics anyway, I wasn't very sure about doing astronomy, but once I had the lecture of astronomy during the Bachelor of Physics, then I was really in love with the subject, and I think it comprised astronomy as the hobby part of going observing at night, but also the the mathematical background and the physics background that I was interested in from high school lectures and so on. So it was the perfect mix, and research has this thing about there is never an end point on your work, right? There is always something new to keep doing, to keep asking, and every question that you try to solve, it just provokes more questions. So this endless loop, I really like it.
Yeah, that's really wonderful that your father took you to that and yeah, and kind of encouraged you to do this, and that you had the opportunity to already discover the early stage in life, that this is your passion. That's really wonderful. And is there maybe a background story about this project? How did this project came about and your curiosity to finding water-rich worlds? And was it something that was, easy to start, or was it, really hard also to get funding for? Yeah, if you could give us some behind the
Yeah, well, this research in particular is kind of a consequence of my PhD thesis. My PhD thesis was focused on the discovery of small planets orbiting other stars, these exoplanets, with new instrumentation that came online at the beginning of my thesis, particularly the TESS mission, one NASA mission that was launched in April 2018, which is when I started my thesis. So mostly my PhD was focused on discovering planets with this new data, with this new space telescope, trying to get some complementary observations with telescopes in the ground, in observatories in Spain and in Chile, in the US. And out of these new discoveries that I did as part of my PhD thesis, it was kind of a natural consequence at the end, just trying to study all of them at the same time, trying to put them into context and try to look for demographic patterns from the sample that we were starting to discover and characterize in a better way. So yeah, it wasn't part of my PhD exactly, but it was a consequence of it. It just took a longer time, and yeah, beautiful paper to write. I did with my PhD supervisor, and yeah, it was a surprising discovery also for us. We were not looking for that, but sometimes just improving your measurements, it leads to reveal patterns that were before hidden in the noise. So that's a little bit the story.
Wow, that sounds wonderful. And yeah, I wanted to check with Victoria. Do you have an additional question you want to ask before we start with the presentation? Victoria, can you hear us?
Hi. Hi. Can you hear me?
Yeah, we can hear you.
Yes.
Okay. Yeah. Maybe go ahead because I didn't hear the question that you asked. I had no sound. I have sound again, but it sounds like you're off to a great start. So unless you have anything you would, like me to ask the usual, but it sounds like you're heading off in a great direction. So I don't know what you asked. In other words,
I tried to replicate your interview, so I hope I do.
it was great. I'm sure.
So,
Go. Yeah. Let's get into the meat of this talk. It sounds exciting. Thank you for the opportunity. Let's go.
okay, so yeah, everyone again for the people that just arrived. There are two versions of the presentation in this Google Drive folder and also in the chat. So there's one version without videos. Then there's a split up PowerPoint version, slide number 1 to 10 and then 11 till end. And if the videos are still slow for you to see, there are separate videos, and Raphael will then refer to them. Thank you.
Okay. So I think I can start by saying that this talk will not focus directly on the paper that Katarina was sharing in the chat. I will talk about it a little bit, but I wanted to give a more general context of this topic because this is a more general audience, and I think it's better sometimes to step back and give a better background than start directly with a very specific paper from a technical journal. So I wanted to talk about the exoplanet field in general and how probably we haven't noticed, but we are living a revolution in terms of the discoveries that is providing in such a young field. And I always start this thing about this concept of revolution because so far we have probably lived two revolutions of knowledge, like two discoveries, two scientific discoveries that have really changed paradigm in the way we see our position with respect to the world and to the universe. And the first of them probably was by Nicholas Copernicus, saying that the Earth is not the center of the universe. That was a concept that completely changed the paradigm of how we see ourselves within the context of the solar system, where the Earth is not the center of the solar system, but is just one of the other planets that revolves around the sun. And within this astronomical concept, which certainly caused a revolution in our way of thinking, I would say the second big scientific discovery or the second big change of paradigm was by Charles Darwin, saying that the the human species, is not a special species; it's just a consequence of evolution and a natural consequence of nature evolution and this thing. This also puts the man also not in the center of being being a special in any way, the same that the Earth is not special in terms of its location with respect to the solar system, and further in the universe, also the human is not special in terms of compared to other living species on Earth. But we are currently living one another revolution that perhaps we have not noticed because we are living in it, which is the exoplanet revolution. So, for the first time in history, we know for certainty that there are more planets out there in the galaxy. This has been a question which is as old as humankind, right? Uh, Thinking if there are more worlds like ours, if our world is special or not. This is a philosophical question that has been posed there since we probably have the possibility of reasoning. But now, for the first time since 1995, it's just a field that has 20 to 30 years, a field of science that is only like 20, 30 years old. We know for the first time, we have the certainty that there are not only planets like ours outside of the solar system orbiting other stars, but that they are more numerous than stars. So we are certain now, we have statistical evidence that there are more planets than stars in our galaxy. So this is a very powerful concept. We are not at the step of saying, answering the ultimate question, which will be, are we alone in the universe? Is there intelligent life or life in the universe? We are not there yet, but we have answered the first part of the question, which is, are there more worlds like ours out there? And this we have been answering. And if you go to the slide number 6, there is a video about a sonification of the exoplanet discovery since the 90s, where this field started, to the end of 2022, where we reached the mark of 5,000 known exoplanets in our galaxy. So this video, it's if you want to see it, I think it's called 5,000 exoplanets, something in the folder, and it will show in with a background picture of the night sky, different points that will be appearing at different frequencies depending on the size of the planet, and different colors indicating what is the technique that was used to discover these planets, how the pace of exoplanet discoveries have been increasing since the 90s to now at a very rapid pace. It's almost an exponential pace that we were reaching 2000 planets by the early 2013 or so, and then afterwards it has been increasing steadily to 5,000 planets, which is the mark that we are currently marking. You see different colors. Those colors indicate the different techniques. Most of the points there are red and blue. Those are the most successful techniques, called the radial velocity and the transit techniques, which we will talk a little bit more afterwards to understand why they consist of. So in the next slide, there is a diagram which is pretty empty, that has in the x-axis, in the bottom axis, it has the period of a planet. The period of a planet is how long it takes to give a full round around its host star. And in the y-axis, in the vertical axis, we have the mass of a planet. It is a logarithmic scale, so it spans a huge range of masses, and it is measured in terms of the mass of the Earth. And the stars that are in this diagram show the location of the solar system planets with respect to their orbital period, which means how long it takes to give one full round around the sun for this planet, and what is their mass. We see the first four planets, the rocky planets in the solar system: Mercury, Venus, Earth, Mars, at low masses down and short periods to the left. And on the right upper corner, we see Jupiter, Saturn, Uranus, and Neptune, with larger masses and at longer distances. In the next slide, you can see the population of the 5,000 exoplanets that I told you overplot in the same diagram. And as you can see, the first striking difference is that even though we have discovered more than 5,000 exoplanets so far, we have been not able to discover any analogs to the solar system planet except for Jupiter. And this is not this doesn't mean that these planets do not exist in other stars. This means that our techniques to discover exoplanets are not very good at discovering planets that are at very long distances or with very low masses. So right now we see there is kind of a diagonal that goes from bottom left to top right, which is a limit in our detection capabilities. However, we see planets of all type of masses. We see planets that are as low masses as Mercury. We see planets that are much more massive than Jupiter in other stars. And we see plenty of planets that are at short orbital distances. But this is a matter of planets that are much, much closer to their stars than Mercury it is to the Sun, with periods that are even sometimes shorter than 1 day, which is this 10 to the 0 in the y-axis. If you go to the next slide, I color-coded the discoveries by their technique. And just to highlight that the transit technique, which is the points in blue, are responsible for most of the discoveries of the short period planets, planets with periods that are shorter than 100 days or so, at all sizes, while the radial velocity technique for most of the discoveries of Jupiter that we know in other stars. Just to briefly explain in each of the techniques, the transit technique, on the next slide, there is a video that is called Transit Method, if you want to see, where it shows a depiction of how the transit technique works. It is a very simple concept, which is that of an eclipse. For an exoplanetary system in which the star, the planets, and our telescope are aligned, we will be able to measure a periodic dimming in the light coming from the star due to the planets that are blocking a part of it. So this technique can measure what is the orbital period, which is the amount that I told you before, how long it takes to give a full round to the star. And also, with very high precision, it's able to measure the size of the planets, the radius. But you need the system, the planet, the star, and your telescope to be aligned with the observer line of sight. And that is unlikely if you go to very far away planets or if you go to stars that are very small. So planets at larger distances also take a long time to cross the stellar disk, and that's why they do it so much less frequently. And because we don't have uninterrupted observations with our telescopes only for some periods of time, it is more difficult, more unlikely to find one of these planets in transit. But the, the technology needed to do that in the next slide is very simple because it's just a camera. So you can use a normal camera, a small telescope, the biggest telescope in the world, a space telescope, whatever. But the concept behind this technique is very simple. You just need to have a camera and observe a star and look for dimmings, decreasing in brightness of the star that occurs periodically. And because of we have CCD cameras and chips that are very big, we can do this even though it's rare to find a planet, a star, and a telescope that are all aligned and perfectly matches and do eclipses from our point of view. If you observe thousands and thousands of stars at the same time, you compensate this low probability of finding a transiting system by observing a lot of systems. So if the probability is only 1%, you do 100 stars at the same time, and then it is likely that you will find one of them showing a transit. Even though all of these stars may have planets, you would only detect one out of the 100, but you can observe the 100. Okay. The other technique that has been very important historically and still today to discover planets is the radial velocity technique, which is a slightly more complicated technique to understand, but there is a video in the folder called radial velocity, or in the slides you can see that that explains slightly better. So the radial velocity technique is based upon the concept of the movement that a planet is inducing in its star when it's orbiting around it. You know that the gravity act both ways. The planet is pulling the star as well as the star is pulling the planet. But the star being more massive, it produces a much bigger pull on the planet than the planet does on the star. But the star still moves around a point in a space that is called the center of mass. And this back and forth movement along the line of sight of the observer produces a Doppler effect in the spectra that can reveal the orbital period and also the mass of the object that is pulling the star back and forth from you. This Doppler effect is the same than we hear the ambulances on the road, and they are starting very with a high pitch, and then when they get far away from us, it is a lower pitch. The same happens with the spectra of the star. If we take the light of the star and decompose it in the spectra, when the star is coming from us towards us, this spectra get shrink. It goes towards the blue. We say it's blue shifted. And then when the star is going away from us in this back and forth movement, the spectra is enlarged and it goes what we call redshifted. This back and forth movement that we will see in the spectral lines, we can infer what is the orbital period and what is the mass of the object that is producing this movement on the star. This technique is not sensitive to the size of the planet, which is very important, and it is why it is complementary to the transit technique. The transit technique gives you the radius of the planet, and the radial velocity technique gives you the mass. But none of them individually can give you both things. And for this, and this is why this technique has had less discoveries, but is the one that is the oldest, it is because we need a spectrograph. And in a spectrograph, we need to observe with a telescope one star at a time. We need to decompose the light of the star with our telescope with a spectrograph, and then we need to compare it with the time, in time, how the star is moving. If we see that there is a periodic movement, then we see that there is a planet in there. So we go to the next slides. This is slide 14, I think. This is a histogram of what is our knowledge of planet sizes in the galaxy. This is a plot that tells you how many types of planets, what is their size, and how frequent do they are in the galaxy. So we see that there are planets smaller than Earth on the left side of the diagram. There are planets even larger than Jupiter. But the most planets that we have found so far in our discoveries, out of these 5,000, most of them are planets that have a size between the size of Earth and Neptune. And those planets do not exist in the solar system. So we do not know what are they made of. Because if you go to the next slide, there is a picture of two balls. Knowing the size of a planet, you have no idea from only the size what is their composition. It's the same that if you look at these two balls, the bowling ball and the volleyball ball, they are roughly the same size, but you know one is much more heavier than the other. So you know more or less, if you only have the size of the ball, you will have no idea of what material it is made of. So that is why it's very important for planets that we do not have any analogs in the solar system, that we cannot send a telescope, a satellite, and check how are they made of. It is very important not to only measure their sizes, but to measure their sizes and their masses, so we can have an idea of what is their density. And for this, you need to combine the two techniques that I described before. You need the radius of the planet from the transit technique, and for this, there are space telescopes like Kepler, the European Cheops mission, the TESS mission from NASA right now, that have been very successful at discovering planets through the transit technique. But then you need to complement them with measurements of their mass. And for measuring their mass, you need spectrographs. And spectrographs, we only have this type of spectrographs in ground-based telescopes. So you will need instruments like Maroon X in Hawaii, HARPS in Chile, Cármenes and HARPS North in La Palma in Spain, or Espresso in Chile, instruments in some of the best telescopes and observatories in the world to do this job. And this is what we did in our paper. What we did in our paper was to combine the measurements of transit and masses from the radial velocity and the transit technique and measure very precise radius and masses to derive densities of small planets that are with the size of Earth and Neptune. So far, there were not many measurements of the masses of these planets because they were small planets and the signals that they produce are very small. But the technology that has been appearing in the last years has allowed us to do these measurements. And in this paper, what we did is refine the measurements and measure the masses and the radii of many planets, and we put them in a diagram like the one in the slide 18. So in slide 18, you can see in the bottom axis the mass of a planet in units of the Earth, and you see on the y-axis the radius of the planet in units of the Earth. So you see a green round circle with a cross that indicates where is the Earth, right? The scale on the y-axis goes up to 4 times the size of the Earth, and 4 times the size of the Earth is approximately the size of Neptune. While in the x-axis, we see planets that are much smaller, much less massive than the Earth, a fraction, a 10% of the mass of the Earth, which is similar to the mass of Mercury, up to 20 Earth masses or something, 30 Earth masses, which is more or less the mass of Neptune. So this diagram encompasses more or less the sizes and masses of planets between the size of Mercury and Neptune, but orbiting other type of stars. And what we see in this sample for the first time is that the planets align very well to only 2 models, which is what they are shown in the slide number 18. We see that you could draw 2 lines and fit most of the planets in this population, but this is not a fit. This is just plotting the models on top of it. So these models, what do they indicate is the relation between the mass and the radius of a planet, depending on what is their actual composition. What are they made of? The green line shows a planet that would be made of 30% iron and 67% rock, which is roughly the composition of the Earth. You see, it passes through the green point, and it passes through almost all of the small exoplanets that we have measured their densities. And then there is another second population that seems to be also very uniformly distributing around this line, which would be a planet that is made out of water and rock in a 50-50 proportion. And this was very surprising because those planets in that regime of the diagram, they were thought to be exactly like the Earth, but with very large atmospheres. So those planets were thought to have a exact same core than the Earth, but we see them with a large size because they have a huge atmosphere made of hydrogen mostly. And that's why, even though they have apparently the same mass, they have a much larger size because the hydrogen atmosphere is so big that you could see a size much larger. However, if you have these planets that are made of, they would have Earth-like cores and huge atmospheres, you would see a big scatter in the population because very small changes in the temperature, in the properties of the star and everything, those small changes in these properties of the planets would make that their atmospheres look larger or smaller. And what they would create is a big scatter around that diagram. However, if you have planets that are so uniformly distributed around this density, it is likely that it's not dependent on having a very big atmosphere, and it is more likely that it is dependent on having a composition that is naturally like that, which is very well reproduced by a 50-50 proportion of water and rock, like the same composition of the comets or some of the icy moons in the solar system. The next diagram, you can see how the distributions, if you plot them in density, which is the mass of the planet divided by its volume, you would see that you can distinguish three populations of planets within this diagram. There is a distribution of rocky planets that have densities very similar to the Earth. They can have slightly more iron, slightly less iron, and that's why their distribution is a little bit more broad. And then we have a sharp peak of planets that are half as dense as the Earth because they are made out of half water and half rock. And then planets that are less dense than that are the planets that were in the top right corner of the previous diagram, that they need to have, additionally of having a rocky or water-rich core, they need to have a big atmosphere because their size is so big that there is no way, there is no model, you cannot make a planet that it is not made with a lot of air to explain their size, which is what we call the puffy subneptunes, because they are more like analogous of Neptune, which has a very big hydrogen-rich atmosphere, and inside it has a water-rich core. How are these water walls that we were so surprised to find? These water walls, how they apparently are, we have no idea. So in the slide 21, I made a diagram of what is the current understanding of how these water walls could be. It could be that these planets are, as we probably are imagining them, they have a core like the Earth, and on top they have a massive water ocean that covers the whole planet and it is very deep. This is the option A. But this option is very unlikely because these planets are very hot, because they are very close to their stars, and it is probable that during their lifetimes, if the water is exposed to the exterior, these stars would have been evaporating the water because the temperature of the most of the sample is very high. It's higher than what the liquid water could survive in the surface of the planet. So it is very likely that the option A, even though it's the one more naturally comes to mind, it is not true. It's not the true composition of these planets. What it is more likely is that these planets are like the option C, which is something like having a core similar to the Earth of iron and rock, and then the water and the rock is mixed. There is, because of the temperature of these planets are very high, especially in the interior, most likely the rock is in a magma form, and magma is very good at trapping water. You can add a lot of water to magma, and magma doesn't change its properties. So what it is likely is that these water walls are probably more like a magma ocean type of planet, where there is a huge global magma lava type of world, but this lava is very enriched in water, at contrary to other smaller planets that we have discovered so far, where they are pure rocks and the rock is so hot it is molten. Here, there is a huge rock. It is probably molten because of the high temperatures, but the content of the magma, it is highly enriched in water. This would be something similar to taking a comet and put it all the way near to the sun and keep it there. At some point, even though it is made out of a mixture of water and ice, it will melt, right? And that's why we think these planets may be like this. So one of the nice consequences of our study, it is the possibility of looking for alternative type of planets when it comes to habitability studies. So the opportunity that water worlds offer is that there are a huge number of planets that are larger than Earth. So if they are larger than Earth, they are easier to observe with our instruments, because of the bigger the planet, the easier it is to detect it with our instrument. And if we can have a lot of candidates of planets that have a lot of water, it is possible that there will be many scenarios in which water could be liquid in some parts of the planet and allow for processes that may allow the creation or the sustaining of life. So this opens an avenue for increasing our sample of candidates to look for life in the future, not only restricting it to planets exactly like the Earth, but also to planets larger than the Earth that has largest amounts of water. And this is something that we are already trying in the solar system, because the moons of Jupiter or the moons of Saturn, which they are having water liquid oceans underneath their surface, which is frozen, because these planets are very far from the sun, so they are not hot enough to having their exposed water in liquid. There are going to be missions that are going to go there and try to see if the water underneath the ice crust, it is likely it is favorable for having life or not. So even in our own solar system, we are looking for alternative type of planets that could harbor life or life species. And this opens up the possibility of having another type of planet, these water worlds, which we could study in the future to see if there are possibilities for looking for life. Just to close, some remarks. In the slide 23, you see a simulation. This is a real simulation with the actual real data of more or less what are the planets that are around the solar system, compared to the stars that are in our solar neighborhood, and compared with the statistics we know about planets. We see that the planets are here depicted in circles. The circle size, it is indicated of the actual planet size. So there are large planets which are like Jupiter size, which are the large circles, which are not that very common, compared to the small circles, which are very common, right? So Jupiters are not that common in other stars, but planets with the size of the Earth, you see there are many. And in red, you can see planets that are orbiting sun-like stars, and then compared to planets that are orbiting other type of stars in gray. So you see, in our solar neighborhood, we are mostly dominated by stars that are not exactly like the sun. Most likely they are stars that are smaller than the sun, even though the sun is a pretty common star. It is not the most common in the galaxy. The most common stars in the galaxy are smaller than the sun. So you see that among all the Earth-sized planets, the ones that are exactly at the size of the Earth, they are color coded exactly darker. In darker red are the ones orbiting the sun like stars and with the size of the Earth, which are analogs of our Earth. And just statistically, if you go to the next slide, you see that very near from us, there will be 1, 2, 3, 4, 5, 6, 7 sun-like stars that have a planet with the size of the Earth on it. So statistically, these type of planets are very likely in our galaxy, even though they are not the most common ones. They are uh, they are likely very statistically common, and that's why looking for habitability prospects in the future with new instrumentation, with new missions that are going to be developed to do that, is going to proportionate ours, perhaps for the first time, an answer, a scientific answer, maybe not a satisfactory answer, about if we are alone in the universe. So I think this is a very exciting time. The exoplanet field started in the 90s and only in 20, 30 years has increased a lot. It has attracted a lot of attention from the astronomy community and the scientific community and the public in general. And I think we have already answered a huge question, which is like, are there more planets like ours? There are. This we are certain of it. And I think within the next century, we will be able to give an answer to if we are alone in the universe. So yeah, thank you very much for your attention, and I'll be happy to take any questions.
Yeah, thank you so much for this really beautiful presentation. This was really beautiful and very informative. So we really appreciate it. And yeah, please, if you have questions, just maybe follow PTR order and unmute and pass down the microphone to the next person. Thank you. So, Denise, do you have a question? Okay. Frank, do you want to start with the questions?
Yeah, sure. Thanks, Katerina. Yeah, I second you. This is beautiful slides and research content. Thank you, Raphael. Uh, this is quite exciting, I think, to learn that. But I do have a few questions. Regarding the slides, I have the slides number somehow one plus yeah, what you're reading out, but the one 18, 19-ish with the scatter plots for radii versus mass.
Yes.
Yeah. So on the slides, I was wondering where is seems there's additional lines you can draw, right? So slightly above, even if you go like even more refined scale, probably there's even more. But there could be one more above the blue line as well. And also,
Uh-huh.
where is Jupiter in this? I'm looking at somewhere very towards the right, but I couldn't see. Is it one of the very large ones?
Okay. Thank you for your questions. Yeah, you are absolutely right. So you could draw another extra line that has a higher slope to fit the planets that are on the top right corner and start to depart from the blue line, right? Those are what we, in the next diagram, what we call the Paphius Neptunes, with this darker blue, in a darker blue in a diagram. What happened with these planets is these planets must have an hydrogen atmosphere. So they are different from the planets on top of the blue line, which they do not have or they do not require having an atmosphere to explain their masses and radii. But when you become so massive as 6, 7 times the mass of the Earth, you see that the population start to stop staying on the lines. This is because the planets are so massive that even a tiny amount of hydrogen that they collect in the disk while they are forming, they do not lose it because their gravitational potential, their gravity is so strong because they are so massive that they can hold on to these light elements. For less massive planets, the gravitational potential is not that strong, and the wind from the star, the energy radiated from the star, and many other processes are able to remove the atmospheres, tiny atmospheres for these planets very easily, especially over the million of years timescales that we are talking here. So that's why the population on the top right, it starts to depart from the lines around 6-7 times the mass of the Earth, which is when they are massive enough to hold on to their hydrogen atmospheres independently of their history and formation and the type of stars they are orbiting and everything. And answering the other question, in this diagram, we only encompass more or less the masses and the sizes between Mercury, which would be in the bottom left corner, more or less, to Neptune, which will be in the top right corner. Uh, Jupiter, for context, would have a radius in units of the Earth of 13 approximately, so it is way high in the diagram. It will escape the diagram pretty much, and in the mass it would be around 320. So also very, very much to the right of what we are drawing there.
Got it. Okay, that's interesting. So they also these massive planets, they have as you explained, they tend to have rings around them. So when it comes to define radius, has kind of becomes a little bit more difficult. But anyhow, so for so now I understand better the. I would like to understand better the composite that your research report, that the 50 and 50, so um, these water war, like what we see from the avatar, uh, are they more seen, more common for the dwarf, for the lower mass sun host, or is it more like less than the less likely for solar type system, right? And how do you depend on what analysis that you can pin down the 50% water?
Yeah, well, these are really very good questions. So this sample, as you mentioned, this is done for low mass stars. This is because our current instrumentation, especially on the mass side, on the radial velocity side, it is much better at measuring the masses of small planets for M dwarfs because of their mass ratio with respect to the star. If you go to larger stars like the sun, uh, we do not have the instrumental precision to measure planets with the mass of Earth or 2 times or 3 times the mass of the Earth. Those are produced such small signals, and usually they are at larger distances that we do not have the instrumental capabilities now to characterize very well these planets. So far, the sample of the M dwarfs, it's kind of complete or free from detection biases. Let's say it is not really true, but compared to the larger stars, sun-like stars, it is true. Where for sun-like stars, if we would plot a similar one, which appears on the paper in the supplementary materials, you would see that the sample, it is limit on the x-axis around 5 Earth masses or something, which is when the populations start to overlap. One thing that is important to notice is these 50-50 planets, these water worlds, they must form beyond the ice line in the protoplanetary disk. This is the distance from the host star where the temperatures are cold enough to have all the water all the water material in ice form, right? So these planets, for having this composition of half water, half rock, they must have formed beyond the ice line, where in the solar system where the giant planets form, right? And then afterwards migrate in, because these planets, we detect them very close then to the star because of the transit technique. What it is important, and we think that this might be a difference for M dwarfs with respect to sun-like star on terms of the population of the water worlds, is the water worlds may be ubiquitous and form as often as the rocky planets for all type of stars, but we will not detect them as likely for one star and the other. This is because we need the planets to migrate all the way in near to their star in order for us to be detecting them with our instruments. So for M-dwarf stars, it's very unlikely that you form giant planets, planets like Jupiter or Saturn. While for sun-like stars, there is more mass, there is more material in the protoplanetary disk, and forming planets like Jupiter or Saturn, it is more likely. And if you form a planet like Jupiter or Saturn, you necessarily need to form it beyond the ice line, and this creates a gap that doesn't move inward anything that is behind him. It's what happens with Uranus and Neptune. They are not near the Earth because Saturn and Jupiter are blocking their path to go inside. But for M dwarfs, because it's very unlikely that they form gas giant planets because there is not that much material in the disk to form these massive planets, it is likely that the planets that form there beyond the ice line, they do not have any obstacles to move all the way to the interior parts where we can detect them afterwards. So I think a big difference that we may find observationally is that the water wall population at close distances to the star is more common for M dwarfs than for sun-like stars.
Right. So okay, thanks for that. And the how do you what is the how do you pin down the 50% water? The by spectral analysis or?
These are just by internal composition models. So these are models that match the density, the measured density of the population. It's an easy calculation in terms of just checking what is the density, fixing the density of a material like that, and then see what is the relation of their mass and radius, taking into account some self-compression and other effects, but it is that. The thing is the 50-50, even though it's just a model that could be 100 or 0 or 70-30, whatever, this 50-50 proportion is interesting because a 50-50 proportion between water and rock, it is what is expected beyond the ice line in a protoplanetary disk from different planet formation models. So that's the composition, the typical composition of a protoplanetary disk beyond the ice line would have a 50-50 content of water and rock by mass. So the observations match this prediction very well from the formation models.
I see. Let me yield my mic, but if there's more time, I do have more questions. Yeah, thank you. By the way, quickly, is the water like in ice form or in liquid form or gas?
Most
Ice form.
likely, most likely mixed with the magma ocean because these planets are very hot. So it is something that we really do not have an analog uh, right now. If they were planets colder than that, it would be likely that they differentiate, but not at the temperatures of the most of the observed sample, which is warmer than much warmer than 100 degrees Celsius.
Okay, thank you. Yeah, I guess Katarina. Yeah, I'll give him a mic.
Oh, yeah, thank you. Dr. Shah, did you have a question?
Yes, I might. Thank you so much, Rafael. We're really learning something new. But my question was that based upon your research, you think that some of the, for example, we have a Hawking radiation, and you think that how it might imply based upon the Hawking radiation, for example, if we want to say how it works around the black hole and those kind of things.
Oh, excuse me, could you repeat the question? My connection was a little bit
Yes, my
unstable.
question is about the Hawking radiation. As we know that it's a kind of the black body radiation and is theoretically actually when we are thinking about, because you just explained about 50-50 portion, and if we just consider the black hole event, so do you think that how it might I mean, what kind of changing or those kind of things gonna happen around the black hole if it just get close to that? Do you have any idea about that?
Well, I do not really know Exactly. I mean, these planets are all detected in the galaxy, in the Milky Way. So the nearest black hole there is, it would be in the center of the galaxy. And these planets are all detected around the solar neighborhood. So it is within, I'd say, 100 light years or something distance from the sun, while the black hole in the center of the galaxy, it is at almost 10,000 light years distance. So the effects that the nearest black hole we know could impose into these planets or this stellar system, it is completely negligible because it would be the same that we would be experiencing. So I do not think so.
And did you identify the form of the liquid in a spherical shape
Oh,
from
we
the
do not know
planets?
how this. We do not know how these planets look like from a close-up look. Those are indirect measurements. So we do not even know how these planets are really made of. What we have is an indirect measurement of what is their density, and their geometry must be globally spherical, but we do not know exactly how the water is distributed because these planets encompass a huge range of temperatures and orbiting different type of stars. So we do not know exactly that. A thing that could help and will help in the very near future will be observations of their atmospheres. So that will be able to distinguish how is the atmosphere of this planet, if they have one, and if they do not have one, because it must be very shallow, and we cannot detect it because we don't have the precision for it, and that can give us some idea of how is the water in the planet, if it is trapped below the surface, or if it is on the surface, or if the water it is mostly in the atmosphere as clouds like steam, and things like this. Atmospheric observations with the James Webb Telescope will be very helpful for this.
Yes, as Frank mentioned, that 50-50 portion is a little bit strange. I mean, proportional, so it just came to my mind. The same question as Frank just asked. So thank you so much. I'm passing the mic to the next person.
Thank you.
Hey, Avis, did you want to ask? Yeah, please go ahead.
Yeah, thanks, Kat. Thanks, Raphael. This has been really interesting presentation, and I really like the slides. Like they're very descriptive. So I do have a couple of questions for you. So I'll probably lead on with this one. So you did mention the transient object approach and the radial velocity approach to trying to
Mhm.
detect like like exoplanets essentially. So I'm kind of curious, is there a potential, um, I guess like, does your prediction is actually like thrown out by, say, for example, if you have like a binary system, or if you have multiplanetary system that can potentially influence gravitationally, or at least like neutrally gravitationally, so that even if we apply like the radial velocity system, where you can depend on the red shift, the blue shift is like the star is actually moving away from us and towards us. Do you see like having multiple objects orbiting around the native star, or even having multiple stars, making predictions a little more difficult? And how do you go about that?
Uh-huh. This is a very good question. Uh, there is no change in our predictions, but it makes things more difficult. So it may change our ability to detect planets. So for the transit technique, it is particularly challenging if the star it is a binary system or a multiple system. So instead of having one planet orbiting one star, we are observing a system of several stars, and they transit each other. So if you have a very big star and a small star orbiting around it, it may look like a big planet. So from a detection point of view, it is difficult to to know with only the transit technique if what you are detecting is a small star orbiting a large star, or if it is a planet orbiting a small star. Yes, because the radius ratio, which is what you measure, it is same. From a multiplanetary system point of view, usually it makes things easier. The more signals you have for a transit technique point of view, the easier is to identify which planet is orbiting each star, if there are more than one star, or things. You would see different events and sometimes even simultaneous eclipses, and that is easy to identify on the data. On the other hand, on the radial velocity side, when you have a multiplanetary system, then you have a very complex signal, because what you will have is a signal from the star or a movement from the star that is the superposition of back and forth movements created by different planets. So it is possible that you create configurations by superposing sinusoids that look like flat lines, and you would not detect a movement at all, even though there are many planets in the system. So yeah, having multiple stars or multiple planets, usually it makes our detections slightly more difficult. So most of our studies so far has been biased towards single star systems, because this is a way, by selecting which stars are we going to observe with our telescope to be single, we eliminate a degree of complication in our analysis. But formation around multiple star system is a very important topic, because the planets that they seem to be detected orbiting multiple star system seem to be different from the ones that we detect around single star system. And this is because the gravity between the two stars or three stars in the system creates so much disruption in the protoplanetary disk that what you are able to form must be completely different than if you have a very quiet environment where things can form steadily and there are not many perturbations of the disk by other gravitational bodies.
Yeah, I fully agree. And also, even if you have like a planetoid um, object that essentially goes to become like a planet, it will have a rather random kind of
Yeah.
orbit, depending on how the two stars are actually orbiting each other. Yeah, makes perfect sense. So, second question is based on the distribution that you have for the planet densities for the different types of planets that you
Mhm.
categorize. So I'm kind of curious, did you actually try to correlate the type of star as well? Like if it's main sequence star, or if it's a brown dwarf that seem to be skewed towards to like specific type of distribution? Does that does my question make sense?
Uh, yeah, we have tried to compare our sample, which is mostly done for M dwarf stars, which are stars that are much smaller than the sun, colder than the sun. We have tried to compare with the stars similar to the sun, and the patterns seems to still be there, but we do not have the statistical confidence to claim as a population that the detections that we see for sun-like stars do not conform a population of also water worlds around them. So it is something that is work in progress for us. We want to try to do the same analysis that we did here, but for larger stars. And for this, we just need better instruments, more precise instruments that can reach the sensitivity that we need to detect these planets that are the same size and the same masses than the ones for the Endors, but the star is larger. So the contrast between the mass of the star and the planet and the radius of the star and the radius of the planet is much larger, and it makes our signals go down. But yeah, we are trying to look for that. We are focusing on small planets. We have not done the exercise for gas giants, because our research interest is on planets that do not have any analog in the solar system. No, that they seem to be so common, and we do not have one of them. So we hope to by understanding the population orbiting other stars, knowing why we do not have one of those in our solar system.
Right, that makes perfect sense. And you cannot actually infer if the planets are tidally locked to their native star, right? At this point, I mean, given the
You
resolution.
can you can do it, and for these M dwarfs, because of their distances to their stars are very close, I would say 80% of the sample of these planets that I showed before in the diagram are all tidally locked. There are some that are at larger distances that perhaps are not, but they are all tidally locked. That's why we are pretty sure that the water walls cannot be something like a huge ocean on top of a rocky core. It cannot be that because these planets being tidally locked and showing the same phase to the star for millions of years, the water, if it is on the surface, it would have been evaporated and create a huge climate that would affect the whole planet on the evolution. So yeah, these planets are definitely most of them tidally locked. When we go to do this study to sun-like stars, then it is likely that we will find planets that are at larger distances, and these ones they will not be tidally locked.
Gotcha. Yep. Final question. Like sort of like something that's been bugging me for a while. We do have super resolution microscopy here that we use for multiple purposes. I'm just wondering why that's not implemented for astronomy, especially like, especially looking into like exoplanets, um, because the aperture size that you probably need would be enormous, right, to kind of resolve these objects. They have to rely indirectly on the transfer object or the radio velocity. But I'm just curious, like, is it a technological difficulty that's kind of prohibiting that? I'm just interested to hear your opinion.
The stars are very far, really, really far. Like the distance, it is enormous. Even the closest stars, we are not able to see them, their size, right? Directly their size, even with the bigger telescopes, even doing interferometry and this type of techniques. So, yeah, it is a matter of stars are so far away that for almost any type of astronomical observation, they are a point source, right? They are a point. And planets are even smaller and they do not bright by themselves. They do not have their own brightness. So you cannot detect them directly, but indirectly. And that's why it is a huge limit. However, there are plans to do much more science with direct imaging. This is a technique in which you point your telescope to a star and then you cover the light of the star with, it's called a coronagraph, but it's mostly like when you put the finger on top of a bulb, a light bulb, and then you can see around it, right? So that's the same technique here. You point your telescope to a star, you cover the light of the star and try to see surrounding if there is something that brights, that glows, which is usually reflecting the light from the star towards you if it is a planet. So there are new advancements to try to use this technique for trying to study analogs to the solar system in the future. Right now, this technique is being used only for detecting stars that are very young, so they are emitting a lot of light and they are illuminating planets that are super big, much larger than Jupiter, and that they are a huge distances from their stars. Long distances from the star, way longer than Pluto or things like this. So these are the only planets that we can detect right now with this technique. Is you cover the light of the star and you are able to see a planet way bigger than Jupiter at a much longer distance than Pluto, which is something that we do not know that exists in the solar system. But slowly, by improving the technology, we will be able to detect analogs to the solar system at the distances of the solar system. So it is something that will be very exciting in the future.
Agreed. I'll pass the mic to the next person. Kyle?
Oh, don't worry, it'll be quick. You all took the good questions that came to mind. I was really taking interest. It was a very vivid presentation. Thank you. I was multitasking and I was still able to kind of track along. And I was curious about the math of the planet to find the density. And then you basically answered the questions about having that placement to be on Earth for uh, the light blocked between the star or the planet in relation to the planet being measured. So, and then you went into, I was going to ask about the Pleiades, because that one was taken, and then you answered about the multi, that would be somewhat of a multi-star environment, would it not? The Pleiades, the Seven
Yeah, well,
Sisters?
this is also a location of planet formation, right? Like it's a stellar nursery, which is at the same time that the stars are forming, planets are forming. So if you have an environment where many stars are formed close together, and many of them are very massive, and they can influence the environments of their neighbors and their disks that are forming around their neighbors, it is very disruptive process that can completely halt planet formation. So a star that is being born very near to a massive star in the Pleiades cluster most likely will not have any planets, because that disk of this smaller star is going to be totally disrupted by the larger star that is near to it. So
Very cool. Thank you so much for the presentation. It was amazing.
Yeah, thank you so much for all those questions and answering those questions. I was wondering, um, that's maybe something, I don't know, maybe very far-fetched, but we had a guest speaker here that talked about white dwarfs, polluted
mhm.
white dwarfs, where you can basically go back in time and assume what type of planets, like maybe assume what type of planets
Falling.
surround it, maybe. um, do you like it, getting more and more of your data with correlating maybe the star data with the what type of planets are around them? Do you think if you would cross link those data sets, you could make better assumptions of both, like what's back in time, what type of planets maybe were around, and if that changed over time? I'd like to learn more about like the evolution of the universe, basically.
Yeah. The problem with the studying the evolution of the universe is that we are part of it, right? So we always need to take a demographic approach to everything, because we cannot wait and see one system how it goes all the way from formation till destruction, right? So it is very difficult to combine the samples because of the different techniques that are used to detect different type of science cases. So for the white dwarf pollution, what you do is you take a spectroscopy of a white dwarf, and you see that a white dwarf can only have neutrons, right? And it's their composition from a theoretical point of view is very clear. And if you go and take a spectra and see something that is not hydrogen and helium, and see things like iron and magnesium, it must be because something fall on top of it, right? Like, and that's the science case for the white dwarf pollution. Is like the white dwarf cannot have this material, it cannot have any iron on it, so this iron must have fall on top, and it still hasn't fall down to the center, and we do not detect it. So, but to combine this information with our current knowledge of planet populations is very difficult because of the techniques that are used and because of the timescales that we are talking about. Even for us, in with the radial velocity and the transit technique, it's very difficult to detect a planetary system that is younger than 1 million years old or 10 million years old. Typically, the system that we are detecting are with the age of the solar system, more or less, like 4,000 million years, like 4 billion years, or something like that. One to 5 billion years old are the system, and and we do not have also the techniques to study the systems that are orbiting stars that are dying, or we haven't been successful at detecting this type of planets. So we do not know if these planets, we are not detecting them because they are not there, or because we do not have the uh, we do not have the necessarily tools or the precision to do that, because these stars are complicated. Very young stars are very complicated because of a lot of stellar activity and things and energy that they expel. And very old stars are also very difficult because they are extremely big, like red giants and things like this. They are huge. And if already we are suffering when we try to find a planet orbiting a star like the sun, imagine for a star that is 100 times the size of the sun. So we have tried, and there has been some results, but not very successful. And that's why the very few detections that we have done, we are not sure if it is because these planets are not there, and that's why they are not common, or just simply because our precision is not enough to do it. But yeah, I think each field is progressing at a very high pace, and everybody is trying to do, at least in astronomy and exoplanet field, trying to do everything as multidisciplinary as possible and trying to combine pieces of information from different fields and everything. So I think slowly, by studying individual cases, we are getting a more demographic view of the planet formation as a whole and planet evolution as a whole. So I think we are going there, but it's still a very recent field. So we are still uh, limited by our instrumental precision, I would say.
Interesting. Yeah, there's also the puzzle of the lithium, the that there's a discrepancy, right?
Mm-hmm.
The Schramm plot. So is there, do you, but if you would just compare that data, like can you see lithium concentrations with your observation, and is there, you know, a discrepancy, let's say, between yours and the white dwarfs, or you know, if you go back in time, because yeah, that it would be interesting too.
Yeah, we in the stars that we have studied, which is mostly Endors and most of the exoplanet hosts, there is no lithium absorption, so we do not find lithium in those stars. And for Endors particularly, measuring elemental abundances is extremely complicated because their spectra, because they are very cold, so there are a lot of molecules and atoms in their atmosphere. In the photosphere of the star, there are a lot of molecules, and this creates bands in the spectra, which is very difficult for analysis to identify single elements. And from our sample, we have no lithium detections at all, but it is very difficult to do this for Endors. So in a sample of sun-like stars, it would be easier to do it. And sun-like stars afterwards are the ones who evolve to white dwarfs, while M dwarfs, they consume their fuel so slowly that in the whole age of the universe, not a single M dwarf has lived the main sequence, right? It has never evolved from that. So our view of the population of M dwarfs is a static view in which most of the lifetime of the star and the planet is of exactly the same one, with the same properties of the star. While for stars like the sun, within several billion years, it is possible for them to evolve and eventually become a white dwarf. And for M dwarfs, it is not possible. So M dwarf, if you focus only on M dwarfs, which was our study, there is it is impossible to try to get an evolution perspective in terms of the future, what is going to happen, because we do not have any examples of old M dwarfs or evolved M dwarfs. So they are just they are just very efficient at consuming their hydrogen.
Oh, thank you so much for, sorry for asking questions that are a little bit far away. And I wanted to ask VTR, you didn't get the chance to ask a question yet. Did you want to ask something before we close the room? Oh.
And no, thank you, Katrina. I was just listening.
Katerina, I have a few more questions if I may. Yeah.
Yeah, Raphael, do you still have a few minutes for Frank's question?
Yeah, no problem.
Okay, thank you.
Yeah.
Go ahead.
Yeah. Hi, Rafael. Yeah, so I've been listening to the previous discussion was also very interesting. I learned a key fact that so these planets are not say there's a fact that due to the tidal lock that the planet will lose its water surface water. Is that the conclusion you share?
At the temperatures or at the distances that we find these planets, it is very likely that that if there was any surface water or exposed water to the irradiation from the star, that would have been removed by evaporation. So what it is left, it must be a small atmosphere which is water rich, but there cannot be below that atmosphere. There cannot be a water ocean as we understand. And
I see.
tidally
Interesting.
locking,
So on
it
the
is a fact that influences it.
I see. So interesting. So on the slides, the 12, that you show the working of radial velocity technique. So
Uh-huh.
I understand. So this there's a wiggly line that you draw. Is can I understand the higher frequency? The highest frequency is one. Um, so it's supposed to be aligned with our line of sight, right? To the
Uh-huh.
observer. Then the highest frequency is one. It's like vibrate towards us, right? So and then
Exactly.
okay, I got it. So the for my earlier question regarding the types of planets that I also see the another plot data, the slides number 9 with and also interesting there's a two color dots, so by two different methods, transit versus radial
Hmm.
velocity. So they both share a seems to be lumped, right? You can say there are three lumps, but say now we only say there are two centers,
Uh-huh.
along the diagonal line. So are they? Although this is for periodicity as x-axis, is it also somehow corresponds to the two type of composition that is this the same grouping as the uh yeah.
Yes, yes, yes. This is totally right. The planets that you see in the diagram, there are three areas, right? There is a elongated area that it is between the size of Neptune and Earth on the vertical scale, but with periods that are shorter than the Earth. This big chunk of planets are the ones that we study here, which are these what we call super Earths or sub Neptunes or water walls or things like this. These other two lamps are the one on top of it that is blue, majority blue. These are the hot Jupiters, the hot Jupiters, planets that are the size of Jupiter, but they are very, very close to their star. Then there seems to be not many Jupiters that have intermediate distances, and then Jupiters like ours in the solar system. So these are the three main classes of planets that we know so far from our observations. So that's why in the diagram in the slide 14, which is the same diagram but seen only from the right, yeah, where you have an histogram by size of the type of planets, but it is corrected by detection biases and occurrences. It is a true statistical number where you see that the Jupiters, even though we have a lot of detections of Jupiters are so favorable observationally that we detect a lot, but this doesn't mean that there are a lot. That's why in the diagram on the slide 14, we see that the planets with a size similar to Saturn and Jupiter, even though we know a lot of them, they are not very common in the galaxy. This is a measurement. The ones that are the most common are the planets that have a size between the Earth and Neptune, which we do not have in the solar system.
I see. So, last question. So, for clarification, so the title of the slides is the water worlds. Worlds. So, are you? So, I'm getting the message that it seems that there's a conflict that the 50% of H2O is more rocky type versus the water world is different from, it's not those water worlds, right? Or I'm misunderstood.
Uh, I don't know. This is a historical name. The water world concept is a it's it was the first explanation that was given in the 2000s for the first planets that were detected with this type of size. So the first detection of planets in the 90s were of Jupiter's, and we started getting better in precision. And suddenly we got to the detection of a planet that had a size of about 3 times the size of the Earth, which is not in the solar system. And one of the first explanation that was given to this planet, it was that it could be fully made of water. It was like a theoretical concept or something like that, but it was meaning that you can get a planet with this size if you just put a lot of water on it. And instead of being made out of rock, if you put a lot of water on it, they are water worlds. And this is a historical name. How they actually look like, it is true that they are water rich in the sense that they were formed beyond the iceland, and they share the same composition that the moons of Jupiter, the moons of Saturn, the internal structure of Neptune and Uranus, which is being rock mixed with water. And this makes it, but in the solar system, this water is in ice form and it is solid and it is much easier to understand. So that's why we call them icy moons, because they are icy. These planets are exactly like the same, but they are so hot that they cannot be icy. But they still have a lot of water. It's just that the water is probably mixed with a magma because the rock is so hot, it also melts. So historically, we have kept the name of water worlds, but I know it is kind of misleading if you think about it. So, and also we do not have, it is something that just regained now a little bit of momentum because this explanation was discarded in the past years. It was mostly discarded that these water worlds could really exist and be ubiquitous. So yeah, we have kept the name for historical reasons in the paper, but it is misleading when trying to think about the structure, the internal composition of the planet. It's true that these planets, these water worlds, they may be more like a lava planet with a lava that is very rich in water.
Got it. Thanks for that clarification. Very, very clear. Thank you. Karina?
Yeah, yeah, thank you so much. We have that kind of water, isn't it when we talk about this deep ocean, like that we have another ocean deeper in the earth, that it's this type of water that's in rock form, basically. Is that, could we imagine that it's very similar to our?
For colder planets, yes. For colder planets that are at a temperature where you could have a solid rock surface. Below that surface, there must be water, liquid water. So for planets that are really, really hot, this rock is also molten, and then there is no possibility. But yeah, we can think for some of these water walls, most likely they are like Europa, Titan, like moons of the solar system are probably a good analogs. Or if you take a comet or something like that, then it's most likely if they are cold enough that they can have a rocky surface. Below that surface, there will be regions where the liquid is water. The water is liquid. Excuse
Oh, interesting. Well, yeah, thank you so much for coming and answering all of these questions that we had. I hope you enjoyed it too. And yeah, and thank you everyone for asking interesting questions. It was such an interesting discussion. Really enjoyed it. So yeah, and we wish you all the luck for your future research and your current research and a lot of funding. And maybe we when you publish some more, maybe we can invite you back, or when you feel like you want to come back, feel free to always come back.
Great. Thank you very much for the invitation. It was fun to be here, discover this platform, and the questions were great. So yeah, thank you very much.
Great, thank you. And yeah, for everyone, if you like discussions like this, if you haven't done so, just follow the club. Then you'll see our calendar, and our next discussion will be led by Dr. Bazou. He will talk about decrypting the mechanical code of DNA and the epigenome. So I think that will be really interesting too. So very different, but hopefully I hear you all back soon, and enjoy the rest of your morning, day, evening, wherever you are. Thank you so much, everyone. I'll
Thank you, Katrina. Thank you, Raphael.
Thank you. Thank you. Bye.
close the room in 3, 2, 1. Bye, everyone. Thank you.